The topic of this video is the eigenvalue distribution of random covariance matrices, known as the Marchenko-Pastur distribution. This distribution has become increasingly important in modern data analysis because it is closely related to the principal component analysis. In PCA, we study the eigenvalue of the sample covariance matrix, and the Marchenko-Pastur distribution tells us the distribution of the eigenvalues when the data is nothing but random noise. So we'll begin with a brief review of PCA to see why this problem is important. Then we'll derive the Marchenko-Pastur distribution using the Resolvent method. So if you watched the previous video on the Wigner semicircle law, you'll see that many ideas carry over. The overall strategy is very similar to the last video. So the difference here is that we are dealing with a sample covariance random matrix rather than Wigner's matrix. Okay, let's get started. Let's first do a quick review of the principal component analysis. So we can start with the data given by a matrix, a P by N matrix. You can think of P being the number of features and N being the number of data points. So let's say that the data is centered, which means the sample covariance sigma equals to 1 over N times XX transpose. So for the principal component analysis, we care about the eigenvectors and eigenvalues of sigma. The eigenvectors of sigma U1 to UP tell us the principal directions. Basically, we want to project data onto those principal directions. So that gives us the principal components. And the eigenvalues of sigma tell us the variance of the principal components. This can be understood with this simple picture. Right, so the PC1 is the direction where the data has the largest variance. And the variance is given by the eigenvalues of the covariance matrix, where the direction of this axis is given by the eigenvectors of the covariance. So the Marchenko-Pastur distribution emerges when the data is nothing but noise. Okay, so let me just write out the statement of the RMT law first. So we can start with a random matrix X. And the dimension of X is P by N matrix. And we want the entries of the matrix to be random. So we want the expectation of the entries to be 0 and the variance of the entries to be 1. And we want every entry to be independent. So the next point is very important. For the MP law to hold, we want both P and N goes to infinity. But the ratio between the P and N, let's denote that with gamma, defined as P over N. We want this ratio to stay somewhere in between 0 and 1. Then the eigenvalues of this of the sample covariance matrix will converge to the Marchenko-Pastur distribution. So the density function of this distribution is given by, so the denominator is given by 2 pi gamma times lambda, and the numerator is given by the square root of b minus lambda times lambda minus a, where a equals to 1 minus the square root of gamma square, and b equals to 1 plus square root of gamma square. So you'll notice here that for this density to be meaningful, right, the lambda needs to stay in between this A and B region. Outside the region, it won't have any density function. So in fact, I have generated a picture for this Marchenko-Pastur distribution that we can take a look together. So looking at this picture, we see that there are two boundaries, A and B. The eigenvalues only has probability inside these two boundaries. Outside A and B, there's no probability density. So another important thing to keep in mind is that this Marchenko-Pastur distribution only shows up when both P and N goes to infinity. So if we compare this with the classical statistics, where we keep the P fixed, or keep the number of features fixed, and only let N goes to infinity. When we calculate the covariance matrix as 1 over N times XX transpose, it will converge to the identity matrix. But for the RMT, the key distinction is that both P and N grows to infinity, where the ratio between P and N are fixed as gamma. That's when the Marchenko-Pastur distribution shows up. Okay, so now let's try to prove this result. So if you watch the last video of the Wigner semicircle law, this proof follows the same structure. We start by writing down the resolvent, R of z equals to sigma minus z times I. Then we take the inverse. Then we can define m of z as 1 over p times the trace of the resolvent. This is also called the Stieltjes transformation. And using the property of the trace, we know that it equals to 1 over p times the sum of the eigenvalues of the resolvent. Then when we have p goes to infinity, that becomes the expectation given some density function for the eigenvalues. Which then we can convert that into an integral. And this integral here can be thought of as some function transformation. We're transforming from the space of lambda to the space of z. So it's kind of like Fourier transform or Laplace transform, where we map the function to another domain. And very importantly, if we look at the denominator of this transformation, we have lambda minus z. And this can be a problem when z is inside the region of the lambda, right? Because that's the case where the denominator will go to 0. And this function will just blow up to infinity. So this is why we always think the m of z as a complex function. So it's a map between a complex number to another complex number. Okay, good. Then for the idea of this proof, so it's very similar to what we have last time. We start with a random matrix X and the covariance matrix. The first step is to use the resolvent. Then by taking the trace of the resolvent, we can obtain some equations about m of z that we can solve. Then we can apply the inversion formula of the Stieltjes transformation to obtain the density function from m of z. So we have shown last time that the inversion formula of the Stieltjes transformation can be written as 1 over pi times the limit as v goes to 0 In here, because z is complex, right? So we can write z as u plus iv. Then we just grab the imaginary part of the function m of z, right? And that will just give us the density function rho of u. So this is the density function for the eigenvalues. Okay, so in terms of this proof, right, let's first think about how we can obtain the function for m of z. So the first thing we can do is to, is to just look at the resolvent. And using some algebraic manipulation, we can obtain a resolvent identity. And that will give us the equation of m of z eventually. So we can start with the definition of the resolvent R of z equals to sigma minus z times I inverse. Then we can move some terms around. We have sigma minus zi times R of z equals to identity. Then we can expand the terms. And we have sigma times R of z equals to identity plus z times R of z. Then we can take the trace of both sides. And we have the trace of sigma times R of z equals to the trace of identity plus z times R of z. Then we can just copy the left-hand side. And for the right-hand side, because trace is linear, we can separate the identity from z times R of z. And this identity matrix is P by P because the covariance matrix is P by P. Right, so the trace of that simply equals to P. And then for the second term, because z is a constant, so we can move it outside the trace. You have z times the trace of the resolvent. And by definition, we know that this equals to P times m of z. Then we can just divide both sides by P. 1 over P times the trace of sigma times R of z. And that equals to 1 plus m of z. So this is an identity equation we obtained by simply manipulating the terms. So see here that we already have m of z on the right-hand side. So all we need to do is to express the left-hand side with m of z, which we will show next. Okay, good. So now let's take a closer look at the left-hand side, right? So let's look at the trace of sigma times R. So the first thing that we can do is just to expand the covariance matrix. So that becomes the trace of 1 over n times the summation xi transpose times R. So we have a covariance matrix times R, right? This is another way to write the covariance matrix, where the xi are data points. So we take the outer product of each data points and then take the average, right? So that gives us a covariance matrix. Then we multiply that by the resolvent R of z. Then because the trace is linear, we can actually separate out. We can move the summation outside, right? So that just becomes 1 over n times the sum of the trace xi transpose R of z. So now we can actually use the cyclic property of the trace, right? The cyclic property is saying that the trace of A times B times C equals to the trace of B times C times A, right? So that just equals to 1 over n times the trace of xi transpose R xi. And we notice here, since xi is a vector, so this is just a scalar. So we can just remove the trace. So that becomes 1 over n xi transpose R xi. Okay, so we notice that this formula has already been simplified a lot. But actually there's a problem because R of z is not so easy to handle. So let me just expand the formula and we can see why, right? So R of z is a resolvent. So we have the covariance matrix as 1 over n times xi transpose minus z times identity times xi. Okay, maybe I should use a different subscript in here. Let me use j in here. And then we have the inverse. So see that a challenge in here is that for every data point, they are both showing up in the in the resolvent and in the outside. And this inverse kind of making everything intertwined together. So a very smart idea here is that we want to separate out the dependency for each data point. And if we look at this equation here, right, we can just ignore the summation for now, and let's just look at this part. Right, we have xi transpose times something times xi. So that is given by one particular data point. But this data point is also used inside the resolvent because we have the sample covariance matrix. And that is exactly the challenging part. So it turns out that a very smart idea is that if we can remove the dependency of that particular data point xi, then that will give us a much nicer form for this equation. So this is exactly where the Sherman-Morrison formula comes in. Okay, so for the Sherman-Morrison formula, the statement is that when we have a matrix A and we perturb that with a rank 1 matrix, let's say that this is UV transpose, and we take the inverse of it, so that equals to the inverse of A, and then minus A inverse UV transpose A inverse, and then the denominator is 1 minus V transpose A inverse U. It's saying that when we perturb a matrix with a rank 1 matrix, you can separate out the dependency in this way. And this is exactly the formula we want to apply for the resolvent to separate out the dependency of the data point I. So in our case, our rank 1 perturbation will be 1 over the square root of n times xi. We multiply that by 1 over the square root of n times xi transpose. So that is one particular data point. And then the matrix A, we can use that as sigma. And then we use a superscript I to denote that we want to exclude the dependency of data point I. And then we want to minus z times I, right? And for here, let me just spell it out clearly, right? So sigma excluding I just equals to 1 over n of sum of j not equals to I, right? And then xj transpose. We're just basically excluding the dependency of one particular data point. And in here, if you look at the formula in here, right, this is just another resolvent, except that we removed one particular data point, right? This is still a covariance matrix. So you can actually denote this formula as as R superscript I. Okay, so now we can apply the Sherman-Morrison formula, right? So that just become R on the, okay, so on the left-hand side, sigma minus Ci is not Ri. The inverse of it is Ri. So that applying the Sherman-Morrison formulas, we have Ri minus Ri, and then we have 1 over n xi transpose Ri over 1 minus 1 over n times xi transpose Ri xi. Okay, good. This is exactly what we want, right? Because now this R superscript I has no dependency on the data point I, where all the dependencies shows up in the second term, right? In this part. Okay, so now we can actually look at this quadratic form, right? So let me spell it out. So the part we are interested in is xi transpose R times xi, right? Okay, so I should be clear here that we just applied Sherman-Morrison formula on the resolvent R. And now we are interested in the quantity xi transpose R times xi. So plug in this equation here. We have xi transpose Ri xi minus 1 over n times xi transpose Ri xi transpose Ri xi over 1 minus 1 over n xi transpose Ri xi. Okay, so that equals to, we can simplify this a little bit. Xi transpose Ri xi minus 1 over n times xi transpose Ri xi square over 1 minus 1 over n times xi transpose Ri xi. So next thing here, you notice that we have this term shows up 3 times, right? This is the same thing. So it turns out that this equals to the trace of the matrix R superscript I, which is approximately the trace of the matrix R. And that equals to P times M of Z. Okay, but let's just slow down a little bit in here to see why this is the case. So let me just take these terms out, right? So we have xi transpose R superscript I xi. We can actually expand this with a double summation, right? So we can use one script as k. So k goes from 1 to p. And then I can use another summation over L, goes from 1 to p. And then we have xik times xil times R superscript I, and then we have KL as subscript. And next, we want to use a property of the random matrix. So the idea is that we first want to separate out the case of K equals to L. So we have the sum of K equals to L equals to 1 to P, and then we have xik square times rkk plus the case where k not equals to L, and then we have xik, xil, and then rkl. So the reason that we want to do this is because we want to use the property of the random matrix, right? Remember that we have the expectation of xik equals to 0. We have the variance. This is just a second moment. Equals to 1. And then we have the independent, right? We have the xik is independent of xil. Right, so we want to use this property in here. Notice that we have two sums over many independent random variables. These are nice because as p goes to infinity, the randomness got averaged out. So these are just approximately their expectations. Okay, so if we look at the first term, a nice way to think about this is that if we multiply and divide by p, then we get an average over many independent random variables. And as p goes to infinity, this average approaches its expectation. So this will just become p times its expectation. I'm not going to spell it out in here. So that equals to, the expectation just becomes 1 over p times the sum of rkk excluding I, right? So that just becomes a trace of the matrix R, which is approximately the trace of R, right? So that's the first term. Then for the second term, it behaves the same because it's also a sum over many independent random variables. And since the cross entries xik and xil are independent, the expectation of each cross term is 0. And when we sum over many independent random variables, they cancel out on average. So this term approaches 0. So that is why this quadratic form equals to the trace of R, which means that our interest xi transpose R times xi equals to p times m of z minus 1 over n times p square m of z square over 1 minus p over n m of z. This is super nice, right? Because we finally have a formula that involves m of z, right? Which means we can bring everything together to get the equation involving m of z, from which we can solve for the Stieltjes transformation of the density. Okay, so now all we need to do is to plug this back into the equation that we have. Okay, I think I screwed up a little bit in here, right? For the Sherman-Morrison formula, this is a plus sign in the denominator, right? This is very important. And we need to change this to a plus sign. So a plus sign here. And then we have a plus sign here and plus sign here. That makes sense. Yeah. So, okay, we can actually simplify this a little bit more. So that equals to p times m of z minus, and then we have p over n m of z square, and then 1 plus p over n m of z. And recall that we defined gamma as a ratio between p and n, right? So you can replace that with gamma, and this just becomes p times m of z minus gamma m of z square over 1 plus gamma m of z. And then we can actually merge the terms, right? So this just becomes p times 1 plus gamma times m of z. And then for the numerator, we just have m of z. Okay, nice. So I think we're ready to write down the equation with m of z, right? Because so for our resolvent identity, right, we have 1 over p times the trace of sigma times r. So that equals to z times m of z plus 1. And the left-hand side is basically can be written as 1 over n times the sum xi transpose r xi, right? So that equals to z times m of z plus 1. Okay, so now we have 1 over n times p, and then multiply by the sum, and then we have p m of z 1 plus gamma m of z, right? Because you see that this equation here doesn't depend on I, right? So we can just replace its sum with n. So that equals to z times m of z plus 1. And we'll see that this np and np can cancel. So our equation just become m of z over 1 plus gamma times m of z equals to z times m of z plus 1. And then we can multiply the denominator to the other side. We have m of z equals to gamma times m of z plus 1 times z times m of z plus 1. So we have a quadratic equation in the end, right? So that's just gamma z m of z squared plus gamma plus z minus 1 m of z plus 1 equals to 0. So this is a key equation, right? So from this is a quadratic equation related to the Stieltjes transformation. So it means that we can solve m of z directly, right? M of z just become, so you have 1 minus gamma minus z, and then you have plus or minus the square root of, we have gamma plus z minus 1 square minus 4 times gamma times z, and the denominator is 2 times gamma times z. And here, if we look at the square root term in here, right? So this square root term actually can be simplified, right? So it turns out that this square root gamma plus z minus 1 square minus 4 times gamma times z, so that can be written as okay. So when we find the two roots, you can write that as z minus a times z minus b, where a equals to 1 minus the square root of gamma square, and then b equals to 1 plus the square root of gamma square. So for this one, I'm not going to show the algebra, but if you just expand the terms, you'll see, right? This is not this is not some difficult algebra to show that. And then also, notice that we have this plus or minus sign in here, right? But for the Stieltjes transform, we only want one branch, right? It turns out in this case, the plus branch is the correct one, because for the Stieltjes transformation, so m of z equals to the integral of rho lambda over lambda minus z d lambda, right? So that behaves like 1 over minus z. And it only can be obtained when we take the plus sign in here. For the m of z, right? So we write that as 1 minus gamma minus z plus square root of z minus a times z minus b. And then the denominator is 2 times gamma times z. Okay, so now we solve the m of z. Right, this is the equation for the Stieltjes transformation of the density function. Okay, so now we just need one last step, right? So that step is to apply the inversion formula from which we can get the density function, right? So, so the inversion formula is given by, so remember that in here we have a complex function, right? It means that z equals to u plus iv, right? And then we care about the case where v goes to 0. So the equation is that rho of u equals to 1 over pi times the limit as v goes to 0, the imaginary part of m of z. So this is the inversion formula we're going to use. Okay, we're almost there. And actually, there are two scenarios we need to discuss. So the first scenario is a case where u is smaller or equal to a, or u is greater or equal to b, right? So this is the case. And this is the case where the square root of u minus a times u minus b is greater or equal to 0, right? We can replace z with u because we only care about the case where the v goes to 0, right? There's no imaginary part. And when we take the limit of that, this square root term is greater or equal to 0, right? It just means that m of z is real, which means that the density function equals to 0, right? So that's the scenario 1. And for the scenario 2, we consider the case where u is greater than a and smaller than b, right? So this is the case where the square root of u minus a times u minus b, the square root term will be smaller than 0. Now m of z is complex. It means that it has an imaginary part. So let's take a look, right? So m of z basically become, we can separate out the real and imaginary part directly. So we have 2 times gamma times z of 1 minus gamma minus z. So that's the real part. And we don't really care about this, right? So we have the plus I times 2 times gamma times z have the square root of z minus a times b minus z, right? But actually in here we can replace z with u, right? Because we only consider the case where z equals to u plus I times 0, right? There's no imaginary part. So I'm just going to replace all this z with u. Now this is very nice, right? So we get so we just basically grab the imaginary part, and that gives us the density function, right? So the density function rho of u equals to, we just divide that by pi, right? We have 2 pi gamma u, and then the square root of u minus a times b minus u, right? And this is exactly the Marchenko-Pastur distribution. This is a full derivation. Okay, and let me just grab the picture one more time. Looking at this picture, we see that there are two boundaries A and B for this distribution. outside this region, there's no probability mass. And then inside A and B region, it is given by this equation in here. So this distribution describes the eigenvalues of a noise matrix when n and p both goes to infinity. Okay, so this entire derivation is pretty dense. So let's just do a quick summary of what we did. Okay, so the key idea of this derivation is very similar to the Wigner semicircle. Okay, so basically we started by defining the matrix X, which is a P by N matrix, and then the Xij, the entries, are independent. Then we have the mean 0, and then variance 1. And notice here, right, we didn't really specify the distribution, right? We don't really care about the distribution of X. In other words, the distribution does not need to be Gaussian. And in fact, there's something deeper underlying this, right? It's known as the universality. So we'll talk about that later in this video series. And then for the MP distribution, right, we're interested in the covariance. So that is given by 1 over n x transpose, what we can spell out as a sum of all the data points from 1 to n xi transpose, right? So these are two ways to write the covariance matrix. And our main target is a distribution of the eigenvalues, right? And our strategy here is to look at the Stieltjes transformation. So that is given by m of z, which equals to 1 over p, the trace of the resolvent. Right, so the resolvent is given by sigma minus zi inverse. And the key step to solve for the for m of z is that we found an equation of it. So the key step that we applied here is that we use the Sherman Morrison formula, right? We use that to handle the resolvent, right? Because it has the inverse. And then after we solved m of z, we can convert that back to the density function using the inversion formula for the Stieltjes transformation. So that's the entire derivation we had for this video. Okay, so in the next video, we'll continue looking at the Marchenko-Pastur distribution, but from a different perspective. So it's quite remarkably that the eigenvalues can behave like interacting physical particles that repel each other. So this allows us to use statistical mechanics to look at the eigenvalues. Hopefully that can give us more intuitions about the Marchenko-Pastur distribution, the eigenvalues, and how they repulse each other in the random matrix theory.